Hi, what I have here on the workbench today is an SG-003A multifunctional signal generator. Believe it or not, I actually meant to get one of these a few months back and do a review on it, as it looked like a very interesting and capable device. But sadly, I totally forgot about it. Anyway, so when an Amazon seller approached me and wanted me to do a review on it, of course, I happily obliged. As usual, I will leave a product link in the video description below. And if you are interested in the product after watching this video, please be sure to check it out. Although the product is marketed as a signal generator, by looking at the specifications here, you will see that this device is actually more in line with a process meter, as it provides precision current output, current sink capabilities, and can also output and measure voltages as well. These features and parameter ranges, such as the 24 milliamps and the 24 volts, are also commonly found on devices that are characterized as loop calibrators. So, in my opinion, calling this device a multifunctional signal generator might actually be underselling it if it can meet all these impressive specifications, considering that a proper process meter can easily cost you over $1,000. It might be that the manufacturers wanted to position this product in the hobbyist market, and if it is labeled as a process meter or a loop calibrator, people may not know exactly what that is. So anyway, that is just my speculation. I just realized the brand name printed on this unit is FNIRSI, as you can see here, which is different than what I thought the seller had mentioned before. Hang on, let me double check on that. Yep, on the Amazon site, the brand name is RIIAI, but the unit looks identical to the one I have here. Now, this practice is quite common among a lot of Chinese product manufacturers, and we have seen quite a few of these examples, including multimeters and oscilloscopes on this channel as well. Anyway, these are essentially the same products, just branded differently. The unit also comes with these 4 color-coded cables with alligator clips, and of course a USB charger and the associated USB cable for the onboard lithium-ion battery. And by the way, the battery life is rated for up to 26 hours of runtime. So even if that time is exaggerated by 100%, it is still plenty by any standard, and I wouldn't worry about the battery life at all. Another thing I wanted to point out is that the manual is not super clear, which is unfortunately quite common for a Chinese product like this. But you do need to read through before using it, as the user interface is not very intuitive given all these buttons here, and these buttons are serving as multi-purpose and contextual buttons as well. So it does take some getting used to, but once you figure it out, it is not all that bad. Looks like the screen protector is still on. Let me remove that. And of course now it's time for us to power it down and take a closer look. The power button is at the bottom of the device, and you can see there's a USB-C port next to it. That USB-C port is for charging the device. According to the manual, you can also use the USB-C port to upgrade the device firmware. By plugging this device into a PC, it will show up as a removable USB drive, and then you can put a firmware onto the drive. Supposedly it will upgrade the firmware. On the top here, you will see there are 4 banana jacks, 2 for outputs and 2 for inputs. That's fairly standard for a process meter like this one. Let me power it up. And as you can see, it powers up really quickly, which is definitely a good sign. Now, by default, it boots into the screen has a split design. At the bottom, these are some of the numbers, and on top, there is a graph. This is where I would say the design is not very intuitive. For example, right now, if you start pressing these buttons, nothing would happen. You really have to refer to the manual. So what I'm going to do here is actually just going to go through some of the main functionalities of this meter, and then we concentrate on some experiments. So the first thing I want to show you is to switch from this display into the digital display. So for that, we press function and we press curve. So now we're in this digital display, and this is what I prefer the most, as you can see everything very clearly. And I don't mind this display at all. It is very crisp. So now let's take a look at some other functionalities. Let's first take a look at the inputs here. Remember, this device we can input voltages and currents, and also output voltage and current. On the input menu, you can see that we have the option for current syncing and input voltage. So there's not a whole lot here, but we do have some settings. Now there's a lot of details here. Obviously, you have to really read through the manual to understand what they are. Unfortunately, as I mentioned earlier, the manual is not that great. So some of these you really have to just try them out. And through trial and error, you can probably figure it out. So that's the input. And let me go out. So now let's go to output. On the output side, you have quite a few more functionalities here. And this one, I believe, is for loop testing. You can output a 24 volts, and we'll see that in a little bit. To the left, we have frequency output. Obviously, you have different frequency ranges. You can use this as a frequency generator, and you can also do PWM as well. So let's go to XMT. Now, I'm not entirely sure what this is, but according to the manual, is for passive current signal testing. And let's move to the voltage. Obviously, you can use this to output voltage as well, which we will also see in a little bit. Of course, you can use this as a current source to output a current signal as well. Already we can see quite a bit of functionality this meter provides. Let me see if there's anything else I forgot to show you that is interesting. Oh yeah, here you can see that we have a calibration for every single measurement here, and that's actually quite neat. If you have a precise enough meter, you can use that to calibrate this device as well by punching in your own numbers here. Okay, let's do some real-world measurement here. And for that, the first thing I want to do is to measure the output using this SG-003A as my current source. For that, I set to output 0 to 24 milliamps, and I hooked up a current meter so we can monitor its output current. So let's go back and let's turn on the output. Oh, we already have some residual current by the look of it, because the setting here is 0. I know the precision of this device, at least from the spec, it says it's plus or minus 5 counts. So this is actually just within spec. Let me increase that by 1, 2, 3, 4, 5. Yeah, so it looks like it is okay. So let's just go to 0.01. It's a little bit out. Let's do a 0.1. So that's okay. Let's go to 1 milliamp. 2. Not bad. 4, 5. So let's go up to 15. And the highest we can go is 25. Oh, 24. Okay. So that is actually not bad at all. And even the simplest current output setting is actually confusing, because if you see here, we have a range. So I assume these are some of the quantization values. And I don't know why you would use that, but you could if you want. So for example, if we go back to output, we can change the actual setting. Let's see if I can figure this out. Yeah, I can change that to range. Whoops, go up. I can change that to range. And if we change that to range, you will see that when we go back to the output, we go back to the output, this actually becomes the 1200 value we saw earlier. The actual current is displayed down here. That's actually not your current. So I'm not sure why you would want to do this. For example, this 600 would be your 12 volts, but I don't know why you would choose this format versus the actual current format. So that is for current output. The next thing I want to do is to test this voltage output. Let me change it to voltage, and I already swapped the leads here. And let's see, oh, by the way, so that is a loop voltage. For the current measurement, right now it's set at 12 volts. You can see it's not quite 12 volts. Nevertheless, that's the setting. I suppose, let's take a look. We can change it to 24 volts. No, it didn't change. Let's go back. Why is that? Okay, so yeah, I have to get out of that menu for it to change. So now you can see the loop voltage is actually changed to 24 volts instead of 12. Okay, so now let's move on to the voltage setting here. And we also want to just output the actual value. So let's go back. So now let's see how accurate the voltage is. Let's turn it on. Let's do 1, 2, 3. So, okay, so let's do 10 at a time. So it looks like there's some threshold under which it doesn't quite register, at least not consistently. So you saw that earlier we were at 0, and when we go up to 5, it's still showing 0.012, and at some point that number jumps. Yep. So it looks like actually the lowest quantization we can have is actually not the last digit here. It's probably 0.01 volts instead of the 1 millivolts here. So that's just my theory here. Actually, no. So when I press this, the last number changes too. At this lower voltage, it doesn't really seem to be that accurate. Change it back to 0, and we do 1 volt. And given what we're seeing here is really borderline of that 0.1% plus 5 counts accuracy here. Let's go up 2 volts, 3. It's actually not that bad, 4 volts. Given that this device is really a sub $100 device, and this is actually quite impressive. 6, 7, 8, 9, 10. You know, in a pinch, you can use this as your voltage reference, I suppose. 20 volts. So let's go all the way to the maximum. 21, 2, 3, 4. Hang on. 23, 24. Okay. I was just gonna say that the 24 is a little bit out. By the look of it, it's not able to output its maximum voltage here. And next I will demonstrate the loop measurement of this device. For that I hooked up the output to the input. So in theory we should be able to measure the generated current using the loop measurement itself. Let me turn on the current and outputting 1 milliamp. Yep, you can see that. The current input is 1 milliamp. 2, 3, 4, not a problem. No problem at all. So let's increase to the maximum current. The reading is a little bit off, but nevertheless, you can measure the current using the device by itself. And now we can use the same technique to measure its own output voltage. Essentially, the sense wire is the yellow wire that is connected to the output of this red wire. So let's take a look here. Let me enable the output. 1 volt. Yep, you can see that. No problem at all. 2, 3, and 4, 5. We'll go to 15. And we know the maximum is about 24 volts. Of course, we can't get that high, as you can see here. We're also measuring the 23.2 volts, like what we saw before. So that is all working as desired. According to the manual, this device can also output a 24 volts via this in port. But the manual is a little bit confusing because it says that the in and COM are internally connected. So let's try buzz it out and to see what the deal is. And right now I am in this continuity mode, and let's see, they are actually not connected. But let me power it on. You can see that as soon as we power it on, these two ports become connected. That tells me that there's an internal electronic switch to switch it on and off. So I assume that in the mode where it's outputting a voltage, these two would be disconnected and connect it to a voltage source. Let's check that out. Okay, so let's change this to 24 volts. So let's see. Actual, yeah. This is a little bit difficult to use. Okay, so in theory, if I press this, it would show up as 24. Let's see. Yep, 24 volts. It's interesting that this is actually above 24 volts. If you remember earlier, we were trying to measure the output voltage. The maximum it seems to be able to output is at around 23.2 volts. So not entirely sure why that is the case. Next, I want to show you the frequency output capability of this SG-003A. For that, I'm choosing the output range. Let's change it to maybe 0 to 200 kilohertz. I'm just thinking that because this meter measuring under 1 hertz is probably not going to be very efficient. Let's take a look here. And let's go back. So right now it's 100 kilohertz. Let's change it to maybe 1 kilohertz. Let's start from there. And you can see that we're outputting a 1 kilohertz signal. Now let's do 2. No problem, 3. And let's just do 10. Yep, works like a treat. 20. And let's do 120. No problem. So let's go to the highest, 200. Yep, clearly this can be used as a signal generator to output the frequency as well. After playing around with this unit for quite a bit, I have to say that I'm very impressed by what this little device offers. And what we have done so far only scratched the surface of what the SG-003A is capable of. So what I'm going to show you next is its ability to convert an input signal into a corresponding output signal. This feature essentially allows you to convert a voltage into a current, from a current into voltage, from voltage into a frequency, or from a current into a frequency. So it is rather powerful. What I'm going to demonstrate here is to show you how to convert an input voltage into a frequency. So for that, all I do is in my input section, I simply select voltage, and in my output section, I select my frequency. And let's change it to 99.99 hertz so that we can easily see the lower voltages. So for that, I'm going to change it here and go back. In order to start the conversion, all I do is press function and press convert. So now the input voltage is converted to the frequency here. To do the test, I'm just going to use my multimeter's ohm range, as that does output a 0.6 volts, roughly thereabout, voltage. Now you can see we are inputting a 0.63 volt, and that gets converted into a 0.63 hertz signal here. And now if I change the output, for example, if I wanted the output to be, let's say, frequency, sorry, it's already in frequency. Let's say if we want it to be current, you will see that when we go back, the output is actually converted into current. Now the reason the voltage dropped is because right now I'm using ohm mode. There is some internal switching. The impedance of this port actually changes between the different switches. So right now that input voltage actually dropped to 0.47 volts, but nevertheless you see the relationship here is the voltage gets converted now into a current instead of frequency. So that is a really powerful functionality. Another feature I want to show you is its ability to generate a PWM signal. So for that, I have configured it to output a PWM signal in a frequency range of 10 kilohertz. And for that, I'm going to enable the output. You will see that right now we are outputting a 10% PWM signal. And the duty cycle can be adjusted to with a precision of 0.1%. So now let's change it to 20%, 30, 40, 50, 60, 70, 80, 90. Now you get the idea. So this is another powerful feature of this little device. Okay, it's time for the teardown. It was relatively straightforward to remove the circuit board from the case. And now you can see that once it's opened up, I disconnected the battery, and here's the battery pack stuck to the back of the case. That is a 3 amp hour LiPo battery, and it's relatively beefy for a device like this. Here is our main board, and we'll take a closer look a little bit later, but right now I want to show you are these 4 banana jacks. Now when I first took them out, I noticed that a couple of these are not securely tightened, so that could potentially be a problem in the long term, because the only thing that is pressing against these contacts are these nuts here. So unfortunately there's no shake-proof washer between the nuts and the contact, therefore I suspect over time they will become loose again. But we'll have to see that. So on this side it's actually quite barren, that's to my surprise, but on the other side there's also not too much either. And the single processor here is an APM32 F103 VC16. So that's an STM compatible processor, and it features 2 12-bit DAC. So those DACs are used to drive the output. Actually, that's quite interesting. Because of the DAC used is 12 bits, the minimum resolution for a 20 volts output is only about 5 millivolts, so I don't know how they get it down to 1 millivolts or thereabout. Maybe there's some kind of a software dithering happening here. If you know what technique they might have used, please leave a comment below. That's the main processor used in this unit. Just zooming in a little bit more, you can see that we have a programming port for programming the processor and also a serial port right here. And here we have an empty footprint. By the look of it is for a switch. Not entirely sure what that is doing there. Maybe there is another layout of the board where the switch is mounted on this side. I don't know. But the switch is actually here. That's the power switch. On this side of the board, there's actually not a whole lot going on. So everything you saw that this device can do was actually implemented in that microcontroller on the other side of the board. Towards the left side, these are the power supply circuitry. This chip is a TP5400. This is actually a dedicated LiPo battery charger, but also provides a step-up voltage of 5 volts to power the other logic circuits. This 8-pin chip here is a 7660, which is a switched capacitor voltage converter that is used to generate the 24 rail needed for the output here. Towards the top, there is a EEPROM chip. By the look of it, it's an ATM-LH430. I think it may be used to store some of the calibration constants used by the processor. We also have 3 of these optocouplers to isolate some of these ports. We also have these 2 op-amps. These are TL0621s. And finally, we have in the middle here, that's a CD406060B, and that is an analog switch, which I think is responsible for switching the ground and this 24 volts port. If you recall, when we power it on initially, these 2 ports are connected, and if we power it off, these 2 are disconnected. And also this port can be switched from being connected to the ground to an independent 24 volts output. So I think that is being switched by this CD406060B here. If you look around these banana jacks, you won't see any protection circuitry on board. For small signal measurements, I don't think you're going to run into any issue, but I would stay away from high energy circuitry when using this device, as there's no protection. If you switch into the wrong mode, you could potentially blow up the board, and worse yet, you might get injured. And that pretty much wrapped up this review. To be honest, I actually don't mind having one of these in my lab. Sure, it is not the most user-friendly device, but it does offer quite a bit of functionality for the money you pay. The voltage and current output capability alone can come in quite handy. Anyway, I hope you enjoyed the video. If you liked the video, please give it a big thumbs up and remember to subscribe to the channel. I will catch up with you next time.